So we plug in our expression for AP function into this quantization condition. And here's what we get. We basically have two integrals. The first one which comes from positive momentum integration. Here it is. It's exponential to minus I over alpha epsilon p minus cp squared over 2 dp over 2 pi plus the same constant times the integral over negative values of p. And the function is slightly different, so as you remember, c is changed to negative c. So it's minus I over alpha epsilon p plus cp squared over 2 dp over 2 pi. So the point is these two integrals can't be taken exactly. So we have to use some kind of approximation. And we know already that our epsilon parameter, our energy, is in some sense a large parameter of the problem. In particular, there is this condition, alpha or epsilon squared over alpha c is big. All right. So we kind of suspect that we have to use some sort of saddle point approximation to compute these integrals, and they look like Laplace type integrals. So why not just try to do this? But before we do so, well, as we remember, Laplace type integral, it looks like the integral of some large parameter times some function of f of z. Here, our parameter epsilon is assumed to be a large parameter, but it's not factored out from this expression. So in order to reduce that exponential into that kind of form, we need to make some kind of rescaling of our p variable. So let's do this. So p is now equal to, well, I don't know, something like beta, where beta is our rescaling parameter, times s. So we plug it into this exponential, and what we get, okay, it's epsilon beta s minus c beta squared s squared over 2. All right, so in order to get rid of this, to factor out everything, so basically we factor out first epsilon beta to get c minus c beta s squared over 2 epsilon. And so we want this epsilon to disappear completely from these brackets. And that means that beta is to be chosen as epsilon over c. And sorry, yeah, right, that's correct. So let's introduce that kind of rescaling and see what happens. So this, for example, let's consider the first integral, this one. So our integral now is equal to the integral from 0 to plus infinity, and now it assumes this classical Laplace type form. I epsilon squared, because one epsilon comes from this factor and another one from beta, right? Epsilon squared divided by c and alpha. And in the brackets, we are left with s minus s squared over 2. And dp is turned into beta ds. So it's epsilon over c ds over 2 pi. All right. And look here. So this is precisely our large parameter of the problem. So it's our big lambda. And now we can use saddle point approximation. So this is our function f of z. Well, in this case, it's f of s. So what we do, we just find the saddle point. Okay, so here it is. F prime of s is equal to 1 minus s. So it's very simple. S is equal to 1. Okay. Oh, by the way, I forgot to mention that f of s is actually not just this function. Well, let's actually write it down. F of s is, well, we have to be very careful. Actually, I made a typical mistake. So I forgot to include this minus I factor. So in fact, f of s is like that. So it's insignificant when we try to figure out where the saddle point lies. This minus I is insignificant, though let's actually write it here. But s is equal to 1. But when we take the second derivative, it's very important to keep this prefactor. So it's now, it's simply I. Right. So now we write down the condition of the steepest descent path direction. As you remember, if our angle of the steepest descent, well, let's denote it as phi. So our steepest descent condition is 2 phi plus the argument of the second derivative should be equal to pi plus 2 pi n. Okay. So what is the argument of f prime prime? Well, f prime prime is equal to I, so its argument is pi by 2. And our steepest descent condition is turned into 2 phi plus pi by 2 is equal to pi plus 2 pi n. And finally, we get our angle. So phi is equal to pi by 4 plus pi n. So now we are ready to use our saddle point technique. So we got this saddle steepest descent direction. So what we need now to draw, we need to draw the complex plane for our integration variable s. And so the saddle is situated, is positioned at point s is equal to 1. And as usual, there are two steepest descent directions. One is pi by 4, which correspond to n is equal to 0, right? Okay. And the other one differs by pi, so by half of the rotation. So it's pi by 4 plus pi, it's 5 pi by O, so it's opposite direction. And now the question is which direction to choose. And so in order to get the correct direction, one needs to keep in mind their endpoints, the start and end points of the contour. So the contour starts at the origin, at 0, and goes to plus infinity. So what looks like just a natural deformation? Well, it certainly seems natural to deform the contour like that. But, well, who knows, probably we could also do it like that. So what is the correct direction? Well, as you remember, we need to draw the so-called allowed regions where the relief of this f of s function, the real part of f of s function, lies below the saddle point. And these regions, so-called allowed regions, they are positioned by 45 degrees from the saddle point, and from the steepest descent path direction. And here they are. So this is the first allowed region. And sorry, yeah, it looks a little bit messy, but hopefully you get the idea. And this is the second allowed regions for our contour. So obviously, if you decide to deform contour like that, so past this saddle point in the pi by 4 direction, like that, so you have to go through this forbidden region where the real part of f of s function positioned above the saddle. So it's not good. So this pi by 4 seems to be the correct direction of our steepest descent. All right. So now we basically use our prepared formula for the asymptotic of this Laplace type integral. So this is our lambda, epsilon squared over c alpha. And we have a prepared answer. So our first integral, I, is equal to square root of 2 pi divided by lambda, which is epsilon squared over c alpha, and times the principal exponential. By the way, we didn't compute it yet. So f of 1, the value of our f function at the saddle, is equal to, okay, it's 1 minus 1/2. It's 1/2 up to this negative I factor. So actually it's minus I by 2. Yeah, like that. And here is our answer. So the exponential so lambda is epsilon squared over c alpha divided by 2 negative I, like that. And yeah, I think that's mostly it. Right, and plus, of course, plus this I pi by 4, the steepest descent direction angle, right? And there is this prefactor, epsilon over 2 pi c. So this is the correct answer for our integral for the first part of our wave function. Now the second integral. The only difference between the first one and the second is their sign change here, as you remember. Right, so let's write it down. So our second integral is equal to, well, it's the integral from minus infinity to 0, epsilon to, we may introduce the same kind of rescaling of our integration variable. So it's going to be like minus I epsilon squared over c alpha multiplied by s, this time plus s squared over 2. And again, epsilon over c ds over 2 pi. And again, we introduce our f function, f of s, now is equal to, as usual, as before, minus I, s plus s squared over 2. We find the saddle, f prime is equal to negative I times 1 plus s. So now the saddle is positioned at point s is equal to negative 1. Now the second derivative, f prime prime, which is simply now minus I, and the direction of the steepest descent. So now the argument of the derivative is minus pi by 2, and the same condition, the steepest descent direction condition, looks like the argument of their f prime prime, which is minus pi by 2 plus 2 phi is equal to pi plus 2 pi n. And here we go. So now f is equal, phi is equal to 3 pi by 4 plus pi n. And here we just have a little space left to draw the correct deformation of our contour. So here is our complex variable s. Here is our saddle, negative 1. And this is our steepest descent direction. So it's 3 pi by 4. It's this direction. It's either this, when n is equal to 0, or suppose n is equal to -1, it's minus pi by 4. So it's the opposite direction. But now the contour stretches from -infinity to 0. All right, so it goes from the left to right. Well, to figure out which direction to choose, again, we shade the allowed regions for our contour deformation. They are positioned at 45 degrees with respect to saddle point steepest descent direction, like that. And now you clearly see that the allowed deformation of the contour looks like this, right? Because the opposite one, when we go from this point to in the opposite direction, well, we'll have to go through these forbidden regions as before, and this is no good. So the correct direction is this, and you can clearly see that it's minus pi by 4. So now we made our choice. Phi is equal to minus pi by 4. And now we have all the ingredients to write down the second asymptotic for our second part integral. So here is our value of f function. It's taken at saddle point -1. It's I by 2. And the integral itself has this classical form, square root of 2 pi over our large lambda parameter, which is epsilon, epsilon squared over C alpha. The modulus of f prime prime is 1. And here is the main exponential, which is lambda times f of -1. So it's I by 2 epsilon squared over C alpha. And we have to add this saddle point steepest descent direction, which was now minus pi by 4. So it's minus I pi by 4. Right. So, and the rest is just this epsilon over 2 pi C prefactor. Okay, and now we basically sum up these two expressions to get this full integral, as you remember. And it should be equal to 0. Right. Well, if you look at the value of the first integral, you'll notice, and compare with the second one, you'll notice that they're simply complex conjugate. So the answer is some irrelevant constant. I call it A, which contains this epsilon or 2 pi C factor. This prefactor, they're essentially irrelevant because the left-hand side is going to be equal to 0, right? So it's simply some constant A times the sum of these two exponentials. The first one is minus I epsilon squared over 2C alpha plus I pi by 4. And the second one is here, right? Okay, so it's I epsilon squared over 2C alpha minus I pi by 4. And what we get here is a simple cosine function. It's 2 cosine of epsilon squared over 2C alpha minus pi by 4. And here's our quantization condition. So this cosine should be equal to 0. And now we get the energy levels. So the argument of the cosine should be equal to pi by 2 plus pi n. So epsilon now n squared over 2C alpha minus pi by 4 is equal to pi by 2 plus pi n. Okay, and right. So that's correct. So now epsilon n is equal to 3 pi by 4 plus pi n times 2c alpha and to the power of 1/2. So these are our semiclassical levels for our problem. So what is interesting here? So as you see, this is, well, it's quite surprising that we managed to find so nicely looking analytical solution. And so I call it semiclassical. Why? Well, you can derive it by yourself, or well, if you have some doubts, let me do it for you. Semiclassical condition means that d lambda over dx is the large scale of your large parameter of your problem. So where lambda is the wavelength of our particle. So lambda up to the Planck's constant is equal to pi over classical momentum. And the momentum, well, let's recall how our Hamiltonian looks like. Hamiltonian is Cp plus alpha x. And classically, that would be our energy of the system. So our wavelength is 2 pi divided by p, which is simply epsilon minus alpha x divided by c. So obviously, if the x, the coordinate, is large, then lambda is small, and this condition is satisfied automatically. So and that means that the motion of our particle is semiclassical for large values of x automatically without any additional conditions. But if x is rather small, then we can actually discard this term, and then this condition gives us the condition for semiclassical approximation. Okay, so let's compute d lambda over dx. So d lambda over dx is, well, we are interested actually in the modulus of this expression. So it's c over epsilon minus alpha x squared, but x is small, so it's basically c over epsilon squared, right? Sorry, I dropped alpha factor here when I was differentiating. So this is our d lambda over dx, and this parameter should be large if we want to use semiclassical approximation. And this was precisely our initial large parameter of the problem. So I think that's it. I hope you enjoyed this physical example and see the power of this saddle point approximation and how it works and how it correlates with semiclassical approximation in quantum mechanics.